Welcome back, everybody. We are going to finish the first half of our unit on exponents, rational exponents, and exponential functions, talking about solving rational functions, graphing rational functions, and all that good stuff. Starting with our properties. So I'm going to fill this in. So this is an overview of everything that we're going to talk about today. How we can solve exponential functions by making like basis, and then the graphs of the exponential functions, how they're increasing or decreasing depending on what their base is, and that their domain is always going to be negative infinity to infinity. Evaluating. Starting with evaluating. Remember, evaluating means finding an answer. So I'm substituting -1 in for x to make this 2 to the negative first power. You can do this either in your head or in your calculator. Remember, the negative, the job of it is to take our base, which is 2, and find the reciprocal or flip it, which is 1/2. Plug in 3, 2 to the third power, and 2 to the third power is 8. Plug in 5/2. 2 to the 5/2 power. Oops, I'm writing a 3 there. Sorry about that. And I plug that in my calculator because I probably have to for that one. And we do roughly about 5.66, and round it to the nearest hundredth place. Putting this in our calculator, 2 to the 4.92 power. We'd write that as f of 4.92. Type 2 to the 4.92 in our calculator, and we get roughly 30.3. So that's evaluating. Evaluating, plugging it into the calculator, or if they're easier numbers, you can try doing that in your head and getting an answer. Exponential functions. Exponential functions for when a base that is greater than 1. Our graph is going to start low and high because this is going to be an increasing function. It is also continuous. Continuous because as I'm graphing this, I don't have to lift my pen or pencil up in order to be able to put the graph on my paper. The domain is always negative infinity to infinity for every exponential function. The range for our parent functions starts at 0 to infinity. We have an asymptote. Remember, asymptotes are those lines that our graph comes super close to, but never touches or crosses. And for an exponential function, it is the x-axis, and that is y is equal to 0. So our asymptotes always have an equation, and for exponential functions, it's y is equal to 0. It'll be different when we get to log equations, but we'll cross that bridge when we come to it. We have 0, 1, 1a. So the asymptote at x is equal to 0, and this point 0, 1. will always be on every parent function, and that's kind of how we can gauge if we have transformations where our graph goes. Our asymptote drives part of our range, because our range will start from our asymptote and either increase if our graph is going up like this graph is. If we happen to have a transformation that reflects our graph, then it'll start from negative infinity to 0 for our parent function. The only thing that changes, all right, so asymptote and range are affected by vertical shifts. And what that would look like, let's say we had 3 to the x power plus 1. Anything that is the same size as our base that we are adding or subtracting is a shift up or down, and that would change our asymptote and our range. In this case, our asymptote would move up 1, so it would be y is equal to 1, and our domain then would be 1 to infinity. This graph is for a base that's between 0 and 1. It's a decreasing function, your decay function. You are losing value as we're working from left to right. The domain, negative infinity, infinity. Again, that's our domain for every exponential function that we have, parent or not. Our range here is still starting at 0 to infinity. This is a decreasing function, decay function, and is still continuous because I don't have to pick up my pencil to be able to graph it from left to right over our entire domain. The x-axis is still our asymptote, still y is equal to 0. These points are still the same as well. Our asymptote is still here. We still have that 0, 1. And everything that we said above about vertical shifts affecting our asymptote and our range still applies, even though this base is a decay base. All right, graph. So we have 1/5 to the x power. When I have a fraction, when I'm looking at my table, I like to keep, if I have to have 4 points, fractions, I like to use the negatives more than the positives, because remember, negative exponents, this is 1/5 to the negative second power. The negative exponent does the reciprocal of 1/5 or flips it. So we have 5 to the second power, which is 25. 1/5 to the negative first is 5. Anything to the 0 power is 1. And anything to the first power is itself. Now, again, you are more than welcome to use your graphing calculators to be able to do this. And I'm only going to do these 3 just because I don't want to make a graph all the way up to 25. Let's be honest about that. And graphing this, I have 1, 5, 0, 1, 1, 1/5, or I'm putting a negative here for. And we're going to make sure that our graph curves that way, but doesn't curve back up, because this is not going to be a parabola. But we also don't want it to touch or cross our asymptote. Make sure you draw your asymptote in every single time. Our domain here is negative infinity to infinity. Our range, our asymptote is still at y is equal to 0 because we haven't had a shift up or down. And so we have 0. Our arrow here is going up, positive infinity. So 0 to positive infinity. Negative 2 to the x power. You can type this in your calculator. If not, then when we're making our table, because 2 is a number bigger than 1, I'm going to keep these positive. This is a transformation. If you put this in your calculator and grab some points, you'll see you find the same ones that I do when I'm done. But I'm starting with 2 to the x power. So 2 to the negative first is a half. 2 to the first is 1. Or sorry, 2 to the 0 is 1. 2 to the first is 2. And 2 squared is 4. What that negative does in front is it reflects our graph upside down. That changes our y values to the opposite sign. So we have negative, 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 negative. Making our graph. Green this time. Negative 1, negative half. 0, negative 1. 1, negative 2. 2, negative 4. Our asymptote. Again, we don't have any big number adding or subtracting here, so our asymptote has not moved. That's still at y is equal to 0. Our domain never changes. It's still negative infinity to infinity. Our range, however, now we're starting, our arrow is down here at the bottom going down, 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 down. That's a negative infinity. And then rising up, rising up, rising up, we're stopped by that asymptote at 0. And so negative infinity to 0 would be our range. This is called an x-axis reflection. Because if you look at our two parent graphs that we made, this took our parent function, which looks like this normally, and flipped it right over this x-axis. So it's an x-axis reflection. And blue. Letter B, 2 to the x plus 3 power. You can put this in your graphing calculator. Otherwise, x plus 3, remember, x's are liars. They always do the opposite of what they say, and this is a left 3. So if I start with 2 to the x on my table, then I would subtract 3 from all of my x values. If I start here, 2 to the negative first is a half. 2 to the 0 is 1. 2 to the first is 2. 2 squared is 4. I subtract 3 from every single one of those x values. I'm not changing these y ones, but negative 1 minus 3 is negative 4, negative 3, negative 2, negative 1. Graphing this, we have negative 4, a half, negative 3, 1, -2, 2, and -1, 4. So you can see that this really did just slide over to the left. So rather than crossing at 0, 1, like we normally would, we're over here at -3, 1. Our asymptote did not change. It's still at y is equal to 0. Our domain still has not changed. There's nothing stopping it from going further to the left or further to the right. And for our range, our asymptote is down there on the bottom, stopping us from going to -infinity. But we can go up top here, and that's an arrow going to positive infinity. Letter C. This -2 is a right 2 because, again, remember, x's are liars. They do the opposite of what they say. And then this -1 is a shift down 1. That also changes our asymptote and our range. So if I start with that 2 to the x parent function, and again, this is assuming that you're doing this without a graphing calculator. If you were doing this with a graphing calculator and you plug that in, you will find these final ordered pairs on your table. 2 to the negative first is a half. 2 to the 0 is 1. 2 to the first is 2. 2 squared is 4. For our transformations, we're going to add 2 to the x because of the right 2 and subtract 1 from the y for the down 1. That makes my new table. -1 plus 2 is 1. 0 plus 2 is 2. 1 plus 2 is 3. 2 plus 2 is 4. 1/2 minus 1 is -1/2. 1 minus 1 is 0. 2 minus 1 is 1. And 4 minus 1 is 3. So again, if you're in your graphing calculator, you should be able to find those points on your table. Graphing those points, we have +1, -1/2, 2, 0, 3, 1, 4, 3. And you can see our graph dip down below that axis. And if you're on a graphing calculator, you're going to see it kind of level out there at -1. So our asymptote is at y is equal to -1. Domain is -infinity to infinity. And our range, well, now our range starts at -1 because that's where our asymptote is. But we still go up to positive infinity. So -1 to positive infinity. Solving. In order to solve an exponential function, we want to get like bases. We're going to use like bases. What that means is I want, like this base is a third and this base is 81. I want those two numbers to be the same number. We usually use the smallest base to start with to see if we can possibly get that to work out for both sides. The only number we can't use as a base is 1 because 1 to any power is 1. 1 times 1 times 1 times 1 times 1 times 1 can multiply it forever and it'll only ever be 1. And so for this left side, I want this to be a base 3. Well, in order to flip this so it's not a fraction anymore, we use the opposite of our negative exponent rule. Right now, underneath here, this is 1/3 to the positive first. So to flip it back up, that's 3 to the negative first. We still have that x out there. And then we want to take 81 and see how many 3's do I multiply together to get 81. Well, 81 is 9 times 9. 9 is 3 and 3. 3 and 3, I have 1, 2, 3, 4 3's. So 81 is 3 to the fourth. Negative 1 times x is negative x. Now that I have our same bases, they're both base 3, we're not dividing by them, we're not proving any magic wands or anything. We're just saying, as long as I know my bases are the same, I can set my exponents equal to each other. We can say negative x is equal to 4. Well, that's negative 1 times x. The opposite is dividing by negative 1 on both sides. And we get x is negative 4. Remember, you can test that by plopping that in a calculator and say 1/3 to the negative 4th power. And do you get 81? And in fact, you do. And so x equals negative 4 is a good answer. We have a base 5 and a base 1 over 125. 5 is my smaller one. Remember, 1 we can't use. So we'll leave the 5 to the x power. Right now, this is 125 to the first power. I want to flip it back up. We use our negative exponent rule to do that. And then I say, okay, how many 5's can multiply to 125? Well, that's 5 times 25. 25 is 5 times 5. I see 3 5's. So we have 5 to the third to the negative first. 5 to the third came from breaking down the 125, and the negative 1 is still there. Exponent rules say we multiply the 3 and the negative 1 together. 3 times negative 1 is negative 3. Now that we have same bases of 5, we can say x is equal to negative 3. These ones are getting just a little bit more complicated, but that's all right. I have a base 2 and a base 8. My smaller number is base 2. I'm going to leave that one alone. We're going to take base 8 and divide it and see how many 2's make base 8. 8 is 4 times 2. 4 is 2 times 2. I have 1, 2, 3 2's. So we are rewriting 8 as 2 to the third power. This is still multiplication, but remember we're distributing now. And so 3 has to get multiplied to the x and the negative 6. The left side we haven't changed. 3 times x is 3x. 3 times negative 6 is negative 18. Again, we're not doing any magic with these bases. We're just saying, okay, if the bases are exactly identical, then I can put my exponents equal to each other and solve for x. I'm going to subtract x to its like term. It's 2x minus 18. Add 18 to its like term. 4 and 18 is 22. Divide by 2 to get x alone, and we get x is equal to 11. You can plug in to the 11 plus 4 and 8 to the 11 minus 6, and you should get the same answer for both to check your work. For the second part of this example, we have a base of 3 and a base of 9. Our smaller number is 3, so we're going to leave that alone. And we know that 9 is 3 squared. Remember, we're distributing. 3 to the x plus 1. 3, 2 times x is 2x. 2 times 3 is 6. Now that these are same bases, we can put our exponents equal to each other. Solve for x. I'm going to subtract x to its like term. We have 1 is equal to x minus 6. Add 6 to both sides, and we get 7 is equal to x. So what happens if our exponent is not a variable? What if it's a number? We are going to use reciprocal or flipped exponents. Remember, our goal is to get our variable alone, which means it would be x to the first power. The reciprocal of 4/3 is 3/4. So if I raise both sides to the 3/4 power, remember the exponent rule is to multiply. 4 times 3 is 12. 3 times 4 is 12. And 12 over 12 is 1. That's exactly what we're looking for. I can go over to 81 and type 81 to the 3/4 power in our calculator. And when I do that, I get 27. We have x to the 2/3 power. The reciprocal of 2/3 is 3/2. So if I raise both sides to the 3/2 power, 2 times 3 is 6. 3 times 2 is 6. 6 over 6 is 1. 25 to the 3/2 power in my calculator is 125. Compound interest. Compound interest we use for anything that we're investing or if we're taking a loan. Starting with P, P is the initial amount that you're investing, borrowing. 1 is always going to be in our problem. It stands for 100% because in theory, you keep 100% of everything that you invest and you're earning interest on it. So that's why it's plus. Or if you borrow money, then you owe 100% of the money that you borrow plus interest. So that 1 stays. R stands for the interest rate in decimal form. And we'll put a reminder on here. Percent to decimal moves. Oops, if I can spell here, I apologize. Moves the decimal 2 places left. N. We have N twice. It's going to be the exact same value for both. And this is the number of times compounded per year. And T is time. Number of times compounded per year means how many times somebody's going to sit down with your balance that you have right now and use this formula to calculate how much you've earned in interest and how much is now in your account. A little list of compounding. Oops, if I can again spell. Sorry about that. Terms. We have annually, which is 1 time per year. So our N would be 1. We have semi-annually, which would be 2 times per year. So N would be 2. Quarterly would be 4 times per year. Monthly would be 12 times per year because there's 12 months in a year. Weekly would be 52 times, and then daily 365 times. They don't use the 1/4 in there. They're just leaving it at 365. All right, so let's try a couple of these. We have $1,000 deposited in account, paying 4% interest, compounded quarterly, 4 times per year. Find the amount after 10 years with no withdrawals. If I'm plugging that into our formula, we have A is equal to 1,000 times 1 plus. Our decimal is here in our percent, so moving it left 2 makes it 0.04 over. N is the compounded quarterly, N is 4. So we have 4 here and 4 up in that exponent, and our time is 10. So that would be to the 4 times 10, or 40th power. I'm going to type that in my calculator, and I get $1,488.86. That's in my account. How much interest is that? Well, we take that $14.88.86 minus the 1,000 that we put in ourselves, and we get $488.86 of interest that we have earned. Finding present value means we are finding P. We know A. I know I want to have this much money in 10 years to be able to buy a house or put a down payment on a house or something. And so if I know my end goal, I can figure out how much I have to put in the bank or money market or whatever it is that I'm investing in to be able to get that amount. So Becky has to pay a lump sum of $6,000 in 5 years. Our A then is 6,000. How much would you have to deposit today, P, at 3.1% compounded annually, so N is 1, to grow to 6,000? Well, that means we have 6,000 is equal to P times 1 plus, our rate is 3.1, 1, 2, so 0.031, N is 1, to the 1 times 5 power, because she has 5 years to do it. Well, in order to solve for P, I have to do opposite operations. Right now, this is P times all of this stuff. And so the opposite of multiplying P by all of that stuff, we divide P by all of that stuff, and then we divide it over on the other side as well. And so we would find out 6,000 divided by all this business with the 1 plus 0.031 to the 5th power. And we end up knowing that we need to invest roughly $5,150, 60 cents, to get $6,000 in 5 years to be able to pay off our lump sum loan. So if we only have 5,000, the annual interest rate, we're not going to do these ones right now. We're going to go all the way to E. In your calculator, over on the far left side, third button from the bottom, the graphing calculator is the LN button. Above that LN button is e to the x. And so if you hit second, LN, and then 1, and hit enter, you get the value of E, which is 2.7182818, and so on and so on and so on. E in nature is kind of like pi in geometry. Pi is a ratio of the circumference to the diameter, and so E is a ratio that we find in nature. If we wanted to compound our money and try to get more money continuously, and so that would kind of be the equivalent of how many times can I hit that equals button as fast as possible, 24 hours a day, 7 days a week for a whole year. Now, we could try to average that out and we'd have a super, super large number, I'm sure, because we're all pretty quick at hitting buttons, especially with texting and things. And so to alleviate that issue, we use this new formula for compounding continuously. P still stands for the initial amount. E is that E in the calculator. R is still the interest rate in decimal form. And T is still the amount of time. So we're still having that same stuff. It's just we're taking out that 1 plus stuff and using E instead. Trying this out, we have $5,000 being deposited. So our P is $5,000. We have our E from our calculator. 3% interest. The decimal is over on the right side. Move it twice. We have 0.03 for our interest. And our time is 5 years. So 5,000 times E to the 0.03 times 5 power. Typing that in my calculator, I find out that my account would have $5,809.17 after 5 years. 8,000 being deposited, we'd have 8,000 E. 5%, moving that decimal twice, is 0.05 times 6 years. Typing that in my calculator, I find out I would have $10,798.87 in my account. So the question is, how much does the compounding really change things? We're not going to do this one. We're going to go over into the $1,000 and plug in $1,000 invested at 4%. $1,000 invested at 4% for 10 years. And when we do those formulas, we have $14.80 and 24 cents for compounding annually. N is 1, so 1 time a year. Semi-annually, N is 2. So if I compound interest twice a year, at the end of the year, we would have $14.85 and 95 cents. Quarterly, 4 times, our balance would be $14.88.86. Monthly, N is 12, $14.90, 83 cents. Daily, 365 times, our N balance would be $14.91.79. And then continuously, using the PERT formula, we would end up with $14.91.82. So the difference between hitting that equals button 1 time a year versus continuously goes from $14.80 to $14.91. So roughly about $11.50. Not really a whole lot. Now imagine if you have a much larger amount that you've invested at a bigger interest rate, that difference will get pretty significant. But, it doesn't really change a whole lot in each of the different compoundings. That's about it for this section. I appreciate you joining me, and I will see you next class. Have a great night.